controls or? That's live right now? Okay. We're getting ready to go live, folks. Hang tight. What time is it now? 10 minutes, all right.
Check 1 2, check 1 2.
Check 1 2. Check 1
Check
2.
1 2.
Salut Simon, comment ça va? Bienvenue. Est-ce qu'on peut avoir ton PowerPoint? Jean? Simon, je sais pas si tu connais
Checking
Simon.
one, check mic
Simon
1
vient
2.
de Ressources naturelles Canada. Elle va présenter aujourd'hui sur les inondations 2019. Est-ce que tu pourrais donner ta présentation aux gens qui puissent la mettre sur... All right, folks, it's just past 1. We're going to ask you to take a seat, please. We're going to get started in a few minutes. Yeah, you're always in the front of the class, eh, Tim?
Maybe not in marks.
All right, well, good afternoon, everyone. Thanks for coming here today. Appreciate it. Does everyone hear me all right in the back? If I need to speak a bit louder? Yeah? The room isn't mic, so. So welcome to our user group meeting, PCI Geomatics user group meeting. We're happy to have you all here today. It's great to see new faces, old faces, and hopefully you'll enjoy the next couple of hours with us here. So my name is Kevin Jones. I'm the Executive Director of Marketing here at PCI Geomatics. Been with the company since 2009. And it's my pleasure to welcome you here and to also have a few of our users who are going to give presentations as part of the agenda this afternoon. It's very, very good to have them here with us. To that end, I would just like to quickly outline the agenda. So we didn't manage to give you a copy of the agenda for today's meeting, but this is roughly what's going to happen. So first up is going to be Arnold Huffam, who's our VP of Sales and Marketing. He's going to talk about some remote sensing trends and some of the responses. Then we have a presentation that's going to be myself and Jean Bouffard, who's our Senior Technical Solutions Specialist, who we're going to talk about the core technologies that we've developed over the last year and a bit. Then we'll have a short networking break. We'll come back. We have our CTO, David Stanley, who's going to talk about the science team, many of which are in the room here, and some of the activities that they're up to. And then we have our two user presentations. So we have CCMEO. They're going to talk about the flood response in Canada, specifically Ottawa and New Brunswick. And then also we have someone from ECCC. Cameron is going to talk about urbanization monitoring using Earth observation. So I just want to ask all the PCI staff to stand for a sec. So I'll go around the room and give a few introductions. So Julius Ostrowski is one of our senior scientists. David Stanley is our chief technology officer. Wessels is one of our SAR scientists, senior SAR scientists. Jean Bouffard is a senior technical solutions specialist. Mazrour Hussein is also a senior scientist. Louis Burry is our VP of technology delivery. Matt McCalla is responsible for quality assurance, basically signs off on the releases when they go out the door. And we have Mauro, who's on video. He works in our marketing team. Arnold Huffam, who's our VP of Sales and Marketing. Selim Ergudin, who is one of our new additions as a technical solutions specialist. Oria Escobar is responsible for sales here in North America and also Latin America. And Jason is responsible for technical solutions as well. So a lot of staff here. You can see we actually made sure there were a lot of different type of staff here at the meeting so you could interact with them. That's what this meeting is about. It's basically an opportunity to meet people who go around the world giving demonstrations and making sure that the technology works for what clients are trying to do. So some of the people like Jean and Jason actually are the people that go on site and give training and make sure that our software works for whatever the solution is. And then you've got some people who are more at the top end in terms of even thinking of what technology should be next, the science team that was here. And then we don't have any actual software developers, although some of the science team does write code. But then after that, we have some QA people who obviously are here, make sure the software that goes out has been rigorously tested. Just a quick note to say that we are live streaming. So we're live on YouTube right now. You can see that I'm wearing a microphone. That's basically for the live stream. We do have a microphone. So if you do have a question, we will come around to you and we'll ask you to speak into the mic so that people who are watching online can also hear what your question was. And for the presenters, if that didn't happen, if you can repeat the question so that our live members can can weigh in on that. And I made a little typo on this. The social media tag is actually, whoops, I gotta edit it here. It's actually, if you do want to take pictures or tweet anything out or what have you, that is the hashtag. Right, Mauro? Yes. Okay. Okay, so at this point, I will ask Arnold to come up. Arnold is going to give you a presentation on some of the latest trends that we've observed in the remote sensing market and what PCI is doing in response to that, and also give you a bit more of a formal welcome and overview of what we're doing here today. You want to mic me out? Yep. Just slip that into your pocket. Tuck the wire away. Okay.
Thank you, Kevin. Good afternoon, everyone. It's my pleasure to be here this afternoon. Finally, we get a little bit of nice weather here in Canada, at least Eastern Canada. Probably one of the coolest springs on record, coolest and wettest. Peter, I see you nodding. Yeah. Hopefully this weather will be with us for a little while and we'll get to see some sunshine and maybe it'll get up above 20 or 25 degrees. Quick note before I get started, at least we do have a couple of people from out of country. The remote sensing industry is full of alphabet soup. Kevin referred to two organizations here in the Ottawa area that we assume everyone knows. One was CCMEO, it stands for the Canada Centre for Mapping and Earth Observation, and the other one was ECCC, I think you called it, which stands for Environment and Climate Change Canada. And I'm proud to be a Canadian that recognizes that climate change is a real thing. So with that, and hopefully I'll be able to make some connection to the validation and measuring the effects, environmental effects of climate change in some of what I have to say here. So, not a new thing. Everyone's been sort of waiting for this moment, or seeing this moment arrive for some time. A first trend that I've seen and we've seen in the remote sensing industry, Earth observation industry, is a plethora of satellites and Earth observation missions. There's a wide variety of ways to look at this, but here's one, and that is it's showing the number of countries participating in Earth observation. It's probably even a little bit conservative at the moment, but we start back in the 70s with the Landsat program, and you can see lots and lots of countries are now participating with national missions, and this slide was done way back in 2017, 2 whole years ago, and I think probably the number has probably increased substantially. I'm not sure entirely whether 197 EO satellites refers to EO missions, because of course the Planet set of missions have added some 150, 200 satellites just with one mission, if you like. Of course, Canada, we added 3 satellites to this on Thursday of last week? Is that Wednesday? Thank you. So I think this number is probably out of date. And just to clarify or categorize this just a little bit, when we talk about Earth observation satellites, we're mainly talking about terrestrial remote sensing. In other words, it's not for weather, it's not for sensing of the atmosphere, it's not for oceans, et cetera, et cetera. So we're talking terrestrial remote sensing almost exclusively here. So here's a trend. It's not actually a trend, and it's an event that happened back in 2008, and that was that the USGS announced that the Landsat data would become free for everyone. And they called it Imagery for Everyone. They put it on their website as such. It's probably an historical page right now. And what happened was that the usage of Earth observation imagery exploded as a result of that policy. Whereas previously, one had to pay for a Landsat image. Subsequent to that announcement, Landsat data became free and open. Somehow or other, the argument was made that it shouldn't be made on a commercial basis. The argument for the platform or the mission shouldn't be on a commercial basis, but on a public good benefit justification. And the downloads have exploded from 53 scenes a day back in the beginning 2000, or when this announcement was made, to now 2017, again 2 years old, at 5,700 scenes downloaded from the USGS website per day. It does not even begin to count the number of replicant sites that are out there. People replicating the USGS database, for example, for their own country, and then downloads coming from that. An example of that would be Australia, for example, that replicated the entire USGS Landsat archive and now distribute through the Australia Geoscience Data Cube in that way. So, so they've moved from 25,000 scenes per year to something like 3 million scenes per year, and that trend has probably increased or continued on into 2018 and 2019. Okay, so moving on from that then, the European Commission and the European Space Agency saw what happened with the Landsat program, and they followed suit, and the Sentinel program has a similar kind of a policy, such that Copernicus program, which includes what we traditionally call terrestrial remote sensing, it clocks out at about 250 terabytes a day being distributed. And here's some numbers for you. There's some 237,000 registered users. Something like 150 petabytes. Those users are downloading 150 petabytes per day. 17 million published products from that, and so on. So, and what this has resulted in is an increase in the usage and of the different Sentinel systems. Sentinel-1 starting in 2015, then and which of course is the radar system. And then 2016, the Sentinel-2 series was added, and you can see the optical usage has started to outstrip the radar usage, or Sentinel-2 is outstripping the radar. So RadarSat constellation missions coming. These trends are continuing, and I hope I don't misspeak the RadarSat constellation mission data policy in any significant way. But the understanding is that our RadarSat constellation mission data will be available free for use for all government use, and Government of Canada use, that is, and all those that are supplying services and products to the Canadian government. So this system, this investment was made by the Canadian government on behalf of Canadians, and the expected usage is expected to go from the initial usage, as you can see there, to 50 times usage under the RadarSat constellation mission domain, if you like. So that increased use of optical data is, Earth observation data is continuing. A little bit drilling down into the RadarSat constellation mission, some key things that we find very interesting about RadarSat constellation mission is that it's going to provide us with daily coverage of either all of Canada or much of Canada. Another interesting factoid there is that it's going to provide exact revisit time every 4 days. So this is as long as you can get image coherence, that this will allow you to do interferometric processing on a 4-day basis within Canada. Nobody's raising their hand to object to my statement, so I guess I got that part right. Okay, so we thought the RadarSat Constellation mission launch was really important. So we made a little event last week where, as the live feed was happening, Kevin and his team did a little RCM launch event online, and we had a few of our experts being interviewed on that. Got quite a number of participants, even if you take out the PCI participants in that. So what's the point of all this? One of the points that I think is really important about all of the data that's now available, much of it available free of charge, a lot of, even at higher and higher resolutions, there's downward pressure on price of Earth observation data in general. And what this has meant is multi-temporal analysis. And all of the single data analytics are still possible under that domain, but the existence of a long archive, and free data policy, and even with pay for imagery domain, cheaper and cheaper, or less expensive and less expensive, is resulting in the possibility of multi-temporal analytics. Now, change detection is not a new thing. I'll tell a war story if you like. Back when I used to work for something called the Alberta Remote Sensing Center, I was doing change detection in an urban environment. Paper here, Procedures for Change Detection Using Landsat Digital Data by Phil Howarth and Greg Wickware, which was published in 1980. Was a guidepost for doing that kind of Landsat-based change detection. And the catch was, back then, that in order to go operational, you had to factor in the cost of the data. And a Landsat image, if memory is serving me right, is depending on the bands that you had chosen, it was clocking in around $4,500 to $5,000 a scene. And so if you wanted to do change detection, you're up to $9,000. And of course, your area of interest was probably always at the intersection of 4 scenes. So just to do change detection, you were into the tens of thousands of dollars just for 2 dates of change detection, which of course is a teeny tiny subset of the concept of multi-temporal. So it's not been practical. This change detection or multi-temporal is not new, but it has not been practical due to data costs and access, arguably until now. Now, one of the missing links, if you like, in the concept of doing multi-temporal analytics is some kind of framework in which to do the analytics. I remember some 5 years or so, we sat down at amongst our technical team and at the executive level at PCI, and we said we need to invest in multi-temporal analytics, and in order to do that, we need something. We need something that does multi-temporal an infrastructure tool that enables that. Dave Stanley's in the room here, and I remember his eyes glazing over, thinking, "Oh, that's a really big deal." Remember that day, David? Yeah. And so after that, I went on a few conferences and went to a conference of GEO, the Group on Earth Observation, and they were pushing something called the Open Data Cube, which is something that came out of the Australia geoscience community. They had come up with something called the Australia Geoscience Data Cube, and they wanted to put it into the open source community, and that's been picked up, and there's an organization now called the Open Data Cube organization, and they're putting that out under free and open source software. And so this becomes an example or a possible infrastructure piece for doing multi-temporal analytics. So what does, sort of getting near the punchline here for some of the development that we've been doing and the product releases that we've been working on, I've just thrown a bunch of alphabet soup at you in this one. I'm saying ODC and MTA need ARD. ODC is the Open Data Cube, MTA is multi-temporal analytics, and we make the argument that ODC and MTA need ARD, being analysis-ready data. And for optical data, this is boiled down to surface reflectance, and for radar data, up to a point at least that boils down to absolute backscatter, at least as a starting point. So in order to get ARD, users will need cross-sensor calibration. I was talking to someone earlier as we started off, where they're doing multi-sensor fusion for mosaics, and ARD would simplify that because of the cross-sensor calibration that would be necessary. Cross-platform calibration. So this means working between sensors as opposed to within a constellation of satellites. Better image alignment, better than just ortho images. Our argument that we've seen and have tested out is that ortho accuracy, at least as published by most of the data vendors, conforms to a certain specification of positional accuracy of a pixel. And it's within spec if it's plus or minus a few pixels, depending upon what the data vendor is and what the application is. But if you a multi-temporal stack from, quote, just orthoed imagery, you're going to find misalignment in the stack. And so we think that better image alignment is necessary and than just ortho. And Jean's going to be, I think, showing you a little bit, yeah. A little bit of that? Okay. And then the users are going to need access to their whole archive. What that means is it exists for, if you want to do open data cube work and multi-temporal analytics, you're going to have to reprocess your whole archive depending upon the nature of that archive. Switching gears just a little bit, it's a rare thing when a customer tells you exactly what they want in a very, very clear way. I hope no one's offended by that statement, but it's really quite something when someone says, yeah, stuff about software as a service and cloud computing and so on and so forth is all very interesting, but what I really want is I want to prototype my workflow on the desktop and migrate it to where the data are in the cloud. In other words, it's not just about all this and software as a service and so on. I've got my crown jewels of my specific workflow, some extra secret sauce that I've added to that process, and I want to create that on my desktop with some prototype data sets, and then I want to shift the whole process into the cloud where the data are. And so we've done some work to enable that. Using Geomatica, using Python, Amazon Web Service, and Docker containers. So getting ahead of myself a little bit, some responses to the trends. First, just as a review, our top level product outline. We have image analysis on the desktop being done by Geomatica. Just as an aside, lots of our customers actually run their Geomatica licenses in a cloud environment. And that's certainly a possible thing. We've developed a package called Geomatica Developer Edition, which is Python enabled, allowing people to develop their applications and then and automate their workflows. And then if you want to go into high volume production, we offer the GXL or Geo Imaging Accelerator. So scalability is possible in both directions. Lots of countries we encounter, they scale up by adding seats, and more in developed world, we see scalability or scaling up through the GXL system. Back to the ARD offering in the context of the data cube, we see GXL as the workhorse for doing pre-processing imagery or for pre-processing imagery. Then a user in our concept would then pass the data and load data into an open data cube. And so we're offering tools to do that, populate the data cube. And then multi-temporal analytics occurs on the right-hand side of this diagram, where we leverage the cube, and we leverage the analysis-ready data. As you'll see in a moment, we're developing tools to both leverage the data cube, as well as making it continuing to make it possible for people to add their own analytics to the data cube. In order to prove some of these concepts, we engaged with a few Canadian organizations. We've got 3 data cube projects running here in Canada. One is a deforestation monitoring project. The study site for that is the oil sands, the Athabasca tar sands, and is for deforestation monitoring. And the cooperating agency, our partner on this, is the Pacific Forest Centre based in Victoria, BC. We've got an urban change monitoring project for carbon accounting. There's a connection to climate change detection and climate change effects monitoring. That's being run here in Ottawa area with Environment and Climate Change Canada. And I gather we're going to hear a talk about that later on this afternoon. And likewise, floodplain risk mapping in cooperation, and we're supporting, of course, the Canada Centre for Observation, or CCMEO. And again, I believe we're going to be hearing from CCMEO later on this afternoon after the break. Okay, so just to review some key technology investment areas, leaving aside the ARD technology or name for a moment, we've always considered image alignment to be of utmost importance. I've been saying for more years than I can count that all the analytics that you do to your data don't matter if you don't get the pixels in the right place. In other words, it's about geography, it's about where that event is occurring, or where that object is. And then normalization, making sure. And so what is this? Alignment is occurring or accomplished using geometric positioning algorithms. We believe that we've got a second to none best in breed reputation for that. We're adding radiometric pre-processing. Why are these important? Images must have high positional accuracy to do change detection and multi-temporal analytics. And we have to, the normalization is done so that we can compare apples to apples. We also add features such as feature extraction and time series analysis, advanced change and anomaly detection. And this is important for understanding and extracting information. And the time series is made possible by big data and the infrastructure that has been developing around big data. And so the ARD part is the top 2 boxes, and the getting things from the imagery happens after that. Okay, so I've been kind of focusing in on this ARD, Open Data Cube, multi-temporal analytics piece that is enabled by the trends that we've observed, the open data policies, inexpensive information, expensive data, as well as accessing a long archive, et cetera, et cetera. We do more than all that. It's not, these are new to us, but that's not everything. We still believe that we're best in breed, and we continue to invest in satellite photogrammetry for both SAR and optical. We continue to invest in advanced SAR processing and analysis, including interferometry. We continue to invest in aerial photogrammetry, elevation model, SEM and DTM extraction, and ortho mosaicing that people have come to count on us for. So then moving forward to where we are here, we've got a user group meeting happening. Last time we had such an event here in the Ottawa area was in November 15th, 2017. We then provided an update on coming technology and what was coming in. Right. So what was coming later, and now we're here to talk about what we're actually releasing. Just a word about our software releases as we look back. In the commercial software world, we have to continually provide commercial software releases, and this is a record of it shows our track record in doing those. The green little flaggy thing shows our annual or big release or annual release. And then the red ones show service packs. So on average, we've been releasing one of these major releases once per year. I don't think that we missed a year in that. It's not always at the same time of year. And if you look at 2019, you'll see that we're generally planning a software in the fall of 2019. So when exactly the fall is, I'm not going to get pinned down on that. We do have a target date, but I'm not going to tell you. Just as a note, we do have the two major product lines, Geomatic and GXL, and as of 2017, we harmonized the release schedules for those two major products. So we love meeting with customers. One of our themes is to get more from imagery. Our focus, of course, continues to be on geoimagery. Just as the marketing pitch, we create and deliver geoimage software products, platforms, and solutions for demanding global customers. That's what we do. But each of these pictures shows where we're engaging with customers. It's pretty small, actually, kind of a showcase of where we're meeting with them. I've got salespeople that are traveling pretty much every week, and events are being done worldwide, either for training, installation, or for marketing events worldwide. We love meeting with customers. If you want to, for us to come and meet with you, we're certainly it's certainly possible, and we're interested in doing so. So it's all about customer engagement and hearing from you what you want. I mean, I kind of put out a challenge there. It's a rare thing when you hear exactly what a customer wants. We want to hear more of that, and so that's one of the reasons we run these events. So with that, Kevin, are you passing the baton, or shall I just go straight to?
We can take questions for.
Oh, okay.
First off, we owe you a hand of applause.
Okay, so Jean, it's my understanding that Jean is drill down and show you a few details about what I talked about and some other things, correct?
Correct, yes.
Okay, so there you go, you got that? Thanks.
Okay. All right, well, good afternoon, everyone. My name is Jean-Sébastien Bouffal, and I'm the Senior Technical Solutions Specialist at PCI Geomatics. And what I'm going to go over this afternoon are some of the core technologies with some live demonstrations of those core technologies that we've been developing over the last year and couple years. And a lot of the technology I'm going to highlight is going to refer back to what Arnold was sort of explaining in terms of trends that we've observed in the industry and how we're addressing those trends. So I'm just going to skip through these right here. So the first trend that we observed in the industry is analysis-ready data. So being able to process big stacks of imagery, doing the geometric and radiometric processing to be able to do multi-temporal analysis and leverage all that data. And the second trend that we were looking at, or we've identified, is aerial production, whether it's DSM true orthos or UAV image processing. And the third one is productivity and automation in general. So there seems to be more and more data that's available, and because there's more access to data, many of our users and customers are interested in automating as much of the processing as possible to go through much more data. So the first topic I'd like to go over is analysis-ready data tools. And that's a package that we released in 2018 to address the ARD market in the Open Data Cube. So Arnold went over this a little bit earlier, but I'm going to go in a little bit more detail about what is ARD. So analysis-ready data, really all it is a trend word for quantitative data. So it's data that's been geometrically processed and rigorously radiometrically pre-processed to a certain standard. And the way I like to think about ARD data is forget the fact that you're looking at a pretty image and think about it as a matrix of measurements. So you have a sensor from space that's taking measurements of the Earth, and we have those measurements. And what we want to do with ARD and ARD workflows is making sure that those measurements are reliable for analysis. So why are we interested in ARD? Well, one of the main reasons is multi-temporal analysis. So when we perform multi-temporal analysis, we often have issues with false positives and a lot of noise. And those false positives and the noise that we get through multi-temporal analysis can originate from geometric inaccuracies, atmospheric noise such as water vapor, aerosols, reflectance of non-Lambertian surfaces, etc. So with ARD, we want to account for all those different factors so that when we do multi-temporal analysis, we're completely eliminating or reducing as much as possible the noise that we get and false positives we get during multi-temporal analysis. The reason why we're interested in ARD is for the open data cube. So if you're going to leverage all this data and put it in a platform to perform analysis, you have to make sure that it's all standardized, the data that you're accessing, all the data that you're storing, and then accessing later on for analysis. And then other applications of ARD, well, from talking to customers, I found out that having pre-processed data helps for deep learning. So it helps simplify the kernels that you develop for, let's say, convolution neural networks, and it helps the process of training your models for deep learning AI applications. Another application is quantitative analysis, physical measurements, and automating image classifications. And I'm actually going to touch base today on automating the image classification process using ARD imagery. So in 2018, we developed the ARD tools. And that's a toolkit that has a number of different functions available for radiometric pre-processing of your data. So with these tools, you're able to access them and make use of them with existing PCI functionality to create these workflows to process your data. And using these tools, at the moment, there are three main products that we're able to produce. We're able to produce a level 1 top of atmosphere reflectance image product, a level 2 standard surface reflectance product, and a level 3 normalized surface reflectance product. And as one thing I also want to highlight, with these tools, you're not just limited to Landsats or MODIS. You're able to use these tools and apply them to a variety of commercial sensors that are available in the market. So I just want to highlight a few tools that are available with the ARD package. And actually, one of them is the multi-resolution analysis, which is not part of the ARD package. It's part of the pan-sharpening package, but it complements the ARD package quite a bit. And multi-resolution analysis is a pan-sharpening technique that's very well known for preserving multispectral values. So if you're going to be performing pan-sharpening on your imagery, you could use a method like the multi-resolution analysis to preserve the multispectral values and perform your analysis afterwards. So here's just an example of a WorldView 3 image. You have the multispectral at 1.2 meters on the left, and then the pan-sharpened product on the right. Now, one tool I want to highlight from the ARD package is our topographic normalization tool. So this is a new tool that came out this year, and it allows you to account for illumination variability depending on aspect and also anisotropic reflectance of different land covers along the slopes with the different aspects. So using this function, you simply need to provide a classification that sort of partitions the landscape based on BRDF reflectance of different land cover and provide an elevation model. So this is the Landsat seen before and after. So by doing this, we're able to normalize the illumination, the varying illumination conditions with different aspects and different slopes. So where PCI fits in with ARD, Arnold already went over this a little bit, but I'm just going to go through this one more time. Big part of ARD is being able to process large quantities of data. If you're performing multi-temporal analysis, you're going to have large volumes of data to deal with. So when it comes to ARD, we have our GXL system that's meant to handle large throughput, well, being able to offer the ability to process high throughputs of data. So that's for both the geometric and also the radiometric pre-processing now. So using GXL, we pre-process the data and we prepare it for the open data cube. Then afterwards, we've made it easy to push the data that we've processed to the open data cube. And once we've established and we've populated the open data cube, we then have the open data cube that we can use, but also we can use Geomatica as an SDK and develop custom function that we could plug into the open data cube and process our data. Now the next feature, next item I want to talk about is Object Analyst, object-based classification. And that's a tool that we released a couple of years ago, but every year we've been improving it year after year. So in 2018, the updates that we've provided for the Object Analyst, well, we have segmentation enhancements. So that has to do with the performance mainly, where we've reduced the amount of memory required to perform the segmentation, and we've also reduced the processing time. And this is important as we're working towards the automation of the object-based classification. Then for the segmentation, we've also to select AOIs to quickly segment only areas of interest for imagery. And then we've provided the ability to import training data and validation samples, and we've opened up our SVM kernel so you can choose different kernels for the SVM algorithm. So just to highlight a few, we have the area of region with the segmentation tool, where you can see right here, I just provide an AOI, and it's only going to perform the segmentation within that AOI. And then we've developed a tool for importing all our ground truth data. So one thing that's sort of convenient with this tool is that we've added the logic to handle when you have conflicting information. And what I mean by conflicting information is when you have truth data that falls in within the same segment. So if a segment was sort of delineated at a very large scale, it's very possible that you're going to include different land cover types and potentially different ground truth data within one segment. So we've added logic to sort of deal with that. Now, another big improvement we've made this year, a new feature that we've added to the Object Analyst, is a SAR package. So this is not just an optical package that's sort of tweaked for radar. This is a sort of solution for object-based classification specifically designed for radar imagery. And we've developed an end-to-end workflow for processing radar imagery in our object-based classification tool. So with this tool, we support different types of polarimetric data. We have full dual polarimetric data, and we also support complex and detected values. And one thing that's very important about this tool is that it's extremely easy to use for non-SAR experts. It's a line process that guides the user from the beginning to the end, where they don't have to do a lot of the pre-processing steps like scaling the data to make sure everything is segmenting properly. We do that behind the hood for you. So to give you an example of our Object Analyst SAR workflow, this is what it would look like here. Let me just move this over. We would start by ingesting our SAR imagery, where we're going to perform a calibration on the imagery and properly import it with all its metadata. And then we would go to the SAR pre-processing, where we're going to perform speckle filtering on the imagery automatically. And then afterwards, we move along to the segmentation process, where we're going to look at all the different polarimetric layers. And then we'll compute some eigenvectors as well for the segmentation. And then once we perform the segmentation, we'll move on to the attribute selection, where we're going to compute attributes and populate those segments with information using polarimetric decomposition and other sort of SAR-specific functionality. Then once we've performed that, we'll continue with the training site editing, the classification, post-classification operations. So that's a high-level overview of the Object Analyst radar classification process. So just to highlight some of the features, here we have the SAR segmentation. And as we open up the tool right here, we can easily access some of the filter types that are available for the speckle filtering. We can choose the Lee adaptive or boxcar speckle filter, the tail trimming, and apply that to the segmentation process. And then we simply need to click on Run, and it will perform the segmentation. And here we have an example of segmentation performed, two different segmentations performed on the same image, but with different parameters. So here we can see the scale size difference, 25 versus 50. So larger scale size is going to allow for more dissimilarity of pixel values within one object. Then we have the SAR attribute calculation. So we're not just computing simple descriptive metrics, the SAR matrices. What we're going to be doing is looking at what type of data you have and offering different sort of metrics that can be computed based on the data you have for you. So this is going to be done automatically, where we're only going to list what is available based on the data you've provided. So if we have full quad pole data, we're able to perform a variety of decomposition parameter methods, as well as looking at texture. If we have only dual pole, well, then we're going to be focusing more on texture and simple descriptive metrics. So with our 2018 release of Geomatica, we call it the Algonquin release. And as we're ramping up towards 2019, it's going to be called the Geomatica Banff release that you can see right here. And with the Geomatica 2019 Banff release, we're going to be focusing on these areas once again, but continuing to sort of develop them even further. So with analysis-ready data, we're going to be focusing a lot more on automation of these processes. With aerial production, we're going to be looking at UAV. And with productivity, we're going to be adding a variety of new features to the software. So now I'd like to revisit Object Analyst and ARD, but through a different lens, through the lens of automation. Because we've done some work recently, working up towards 2019, where we've automated a lot of the analysis-ready data production and also the object-based classification. So starting with ARD automation, so actually let me take a step back. With ARD automation, I mentioned this earlier, it is important that we automate the entire process because the entire purpose of this is being able to process large volumes of data for multi-temporal analysis. So we've done work recently within the GXL system where we've automated a lot of the surface reflectance products that we're able to produce. So as we're working towards the automation of ARD products, one of the main things that we're doing to drive processing are pre-spectral classifications. And one way in which we're using these pre-spectral classifications is by creating these exclusion masks that guide where we're collecting points and where we're sampling, as well information for regression analysis and other things that we're doing. So with these automated exclusion masks, we're able to take a satellite image and automatically produce this pre-spectral classification and then use this information to sort of isolate and exclude areas that we don't want to consider for, let's say, point collection. We don't want to collect GCPs or tie points on clouds or in water bodies. So using these masks, we'll exclude those areas. Or if we're doing some sort of linear regression, we don't want to consider certain areas as well. Or we want to limit ourselves to certain areas. So a lot of the automation that we're doing with ARD is driven by these pre-spectral classifications. Now, one of the first methods that we've developed for automating the ARD products that we're doing is normalizing imagery to MODIS as a reference. So performing regression between our target imagery and a MODIS product that's already been pre-processed quite rigorously. So what we've been doing is taking these MODIS 16-day composites of MCD 43A4, and then we've been correcting our data to that product. And this is done entirely automatically using the GXL system at the moment. So what we've been doing is using APIs, automatically downloading data for the data that we're processing, and then pairing that data with the imagery, and then performing regression analysis to produce a surface or a spectrally normalized reflectance product. So this simply goes through the process once again. So we perform spectral correlation between our MODIS and our target products, and everything is done automatically. We're just downloading the imagery, pairing it up, and performing regression analysis to get a surface reflectance product that's normalized to MODIS. Now, we're not only automating the radiometric pre-processing, but we're also automating the geometric corrections. So we've already automated in the past the GCP collection, tie point collection, and ortho production. But what we've now introduced is a new process called super registration. And this super registration process comes after we've done the orthos and the point collection. So Arnold kind of touched base on this a little bit, but what we've noticed, you may those from different sources, and when you compile them together, you'll notice inaccuracies and sort of offsets between them, misalignments. So depending on the DM that was used, the accuracy standards, the viewing geometry of all the different images, you could have differences between all these images that you want to analyze. So we have a new process called the super registration that's going to automatically go through an entire stack of all your images and make sure that you have subpixel alignment. So this comes after the process, where we're sampling all these images and making sure that we're aiming for about a third, a fifth, and even 1/10 of subpixel accuracy. Because from doing certain analysis of, doing certain examination of radiometric differences based on offsets, we've noticed that it is quite important to have at least a fifth to a third of subpixel accuracy. So here's just an example of the super registration process, where we have our reference image, we have our original ortho, and then we have our super registered ortho. So we had a 1 pixel shift right here, and we're able to automatically correct it to our reference. Pardon me. Now for the feature, on the feature extraction side and the object analyst side, in 2019, we're going to be making available the ability to automatically perform object-based classification. So I'm going to go through that right now and explain how we're doing that. So now later in Geomatica 2019, we're going to be able to use the object analyst tool in 3 different capacities. The first one, you'll be able to use it with manual interactions. Well, a manual interaction, which is more process, well, you'll use a tool, you'll go through it step by step as an operator. And then the 2 new capacities that we're providing is either using our focus tool to automate the process using the UI, or working on an algorithm level to automate the entire object-based classification process. So one of the reasons why we felt an area to sort of develop is because with object-based classification, you're not typically, well, with any classification endeavor or project, you're not really limited to one image. What you do on one image, you want to be able to reproduce that for a large spatial extent or a large multi-temporal extent. So part of developing this new tool was essentially just to scale up. So the way we're able to scale up or reproduce the classification or automate it, well, we start off with step 1 where we're training the model. So we're going to begin by taking one image, one scene, or multiple, doing a segmentation, calculating the attributes, and then collecting training data to train the model. Then once we're content with the model we've trained, then we're able to move on and apply that model to automatically classify all other images. So the process is very similar to what we've had before for the object analyst, where we begin with the segmentation. We calculate the attributes objects. We do the training site collection. But now when we do the supervised classification, it's going to produce a text file that has the model, the SVM model that we've trained for classification. And using this trained model right here, we're going to be able to apply that iteratively afterwards to all our images. So for example, we start off at step 2 right here. We have our model, and we just plug it into the workflow. And as we go through all these functions right here, it's just going to read the model and produce all our, it's going to classify all our images automatically for us. And I'm going to provide a demonstration of that momentarily. So here's just one example of using the Object Analyst tool for batch processing, but inside of Focus. So okay. Don't think it wants to play. Pardon me?
Do you have to OK the panel?
There. It's working on YouTube? Oh, okay. Okay. Well then. So we'll just skip ahead and go to the live demonstration. So as a live demo, what I want to, well, a very high level demonstration, what I want to demonstrate is the automated ARD, some of the tools that would be used to perform, well, to automate the production of ARD, and also the automation of the Object Analyst. And the reason why I chose to highlight the two features is because they work together. If you want to successfully perform object-based classification in a consistent manner, it's very important that you pre-process and you normalize your data ahead of time before you move on to that step. So I'm going to begin in GXL, where we have a lot of these automated tools available for the radiometric pre-processing. So for those of you who have not seen GXL before, this is GXL. It's a sort of server-side application for processing imagery. So here I logged into my GXL. And what I'm doing now is only 3 main things. So in this demo, I'm actually using Landsat data, so it's already been orthorectified. But what I'm doing is simply applying super registration to my data to make sure that it's subpixely aligned. And then afterwards, I'll download all my MODIS imagery automatically and then perform the spectral normalization to MODIS. So to do this, it's quite simple. I go to Create Job, and I'm going to go down to super registration. So apply super geometric correction to multiple orthorectified images. Inside the super registration job, I simply provide the input folder for my orthos, specify an output, and then I choose a reference image that I want to register to. So that could be the first image in a time series stack, or it could be an independent reference image that I have for registering to. And once I've provided the input, the output, and the reference, I simply click on Submit, and it's going to automatically super register all my images in a time series stack. Now once that's done, I move on to the next step, where we have a download scenes job now in GXL that's available. And this job right here is going to automatically download all the MODIS imagery I need to normalize my imagery. So for this job, I simply specify an output folder, and I can specify some information for the acquisition dates, the tile numbers, or I could select an AOI. I could choose to use MODIS or other imagery that's available from different APIs, provide the dates, and just submit the job, and it's going to automatically download the imagery that I need. So this step completely automated again, and then the last step is a spectral normalization to MODIS, where I choose spectral normalization to MODIS. And for this step right here, I would choose the input orthos that are my super registered orthos, the folder containing all the MODIS imagery, and then one output folder, and that's it. And then everything is done for you automatically. So that's the process right now that we have in place for producing ARD data in an automatic manner. So now if I open up Focus, here I have an example of all these super registered, spectrally normalized Landsat images that I have available right here. So this is the data that I prepared for my automatic object-based classification. So if I just zoom into some areas, we can see right here that everything is perfectly aligned to each other. I'll zoom in a little bit closer. Now with Landsat, it's not typically an issue that you would have offsets, but for other sensors, it can be. And this job will make sure that, well, the super registration process will ensure that you do have subpixel accuracy. So this was the first component, the automatic ARD portion. So now that I've prepared this imagery, now I could begin performing analysis on it. So I'm going to demonstrate how you could use the Object Analyst tool to perform automatic object-based classification. So the first step, you're going to begin with one image. So right here I have the city of Calgary, and I'm going to train my model with this first image. To do that, I'm going to open up the Object Analyst tool, and I'd followed all the steps as I would normally if I was just manually using the tool. So I begin with the segmentation process, where I choose my image, and the channels that I want to use for the segmentation, the parameters, and then I would start the job and perform the segmentation. Then I continue down the workflow. I calculate the attributes that I want to use. And then we get to the most important part for automating the object-based classification, and that's selecting your training data. So to do this, we're going to use the training site editing tool that's available in Object Analyst. And using this tool, I'm going to, well, first of all, I'm going to establish my classification scheme, and then afterwards, I'm going to collect objects for each one of those classes. So for this demonstration, I'm more interested in the impervious urban surface in the imagery around for Calgary. So I have some very basic class, open water, impervious urban, coniferous/deciduous, mixed agriculture and grass, and agricultural bare soil. So now using this tool, I would simply collect my data. And it's important that you collect good data at this process because this is what's going to be used to train your model that would be used for all the subsequent classifications afterwards. So once you've collected all your training data and your validation data, I would continue down the process to the supervised classification. And at the bottom, you'll see that there's Save SVM Training Model. And I'm just going to provide an output text file where it's going to save my model that I've trained right here with the SVM and the data that I've collected. And then I'll run that once. And once I've performed that classification, I'm then ready to apply that to all the other scenes or tiles that I have available. So for automating the classification, I chose the approach to use Python. So all the functions that we need for the automatic object-based classification are available in Python. So to do this, let me just go back. To do this, I would first select my folder, or create a variable for my folder that contains all my images, an output folder. I'll use the first segments that I created as a template. I specify my SVM model file, which I'll highlight right here. So when you go through the training process, it's going to create this text file that has the hyperplanes for the SVM. And then afterwards, I set ancillary data information as well for the process. So I just need this simple information right here, the SVM file. And there's three main processes to run. I've created functions for them. There's the segmentation process that I've written function for right here. There's the attribute calculation process that I've written a function for right here, and then the run classification. So there's three main Geomatica functions for automating the object-based classification. So what I've done is create a script where I'm going to go through a folder, find all the files that exist, create a list of all those images, and then I'm going to iterate through that list, running these three functions for each image. And that's essentially the process for automating the classification. So now if we go back to focus, here's some of the results of the automated classification. So my first image, my Landsat scene, was acquired in 2014, and my last one was acquired in 2018. So you can see right here that just flickering between the two images, there's a significant amount of land cover change that has occurred around Calgary. So now I have that change. Well, I have sort of inventory of the land cover quantified over different dates. So starting from my 2014 classification, we can see we have our impervious urban area right here. And as I go to 2017 and then 2018, we can see the urban area growing outwards for Calgary. And these classifications right here are performed completely automatically using Python and the object analyst functions. Any questions about that before I continue? Okay. So one of the reasons why I wanted to show the automatic ARD and the automatic object-based classification is because they do work together. It's important to pre-process your data before doing any processing or analysis afterwards. Okay. Now the last section I'm going to continue on is aerial production. So leading up to 2018, we've done quite a large number of improvements for our aerial technology. And some of the main products that we're now able to produce with our aerial package, while we have our multi-view DSMs, we have the ability to produce terrain models automatically. And then we have three different types of orthos. We have DTM orthos, we have DSM true ortho, and we have true ortho images. The difference between the DSM true ortho and the true ortho products, well, one's produced using a surface model, and the other is produced using building models. And then ortho mosaics. So I'm just going to run through the aerial package right now and highlight some of the new features that we have in 2018 and some of the features that are important with the aerial package. Pardon me. So in this slide right here, we have sort of a standard aerial workflow. And what we sort of highlight in this workflow right here are some of the QA tools that we have available for the aerial workflow. So for the DEM extraction process and preparing DTMs, one tool that's very important is the DM editor. So the DM editor will allow you to manually correct artifacts and filter your surface model to produce a terrain model. And one key feature that's very important with the DM editor is the ability to view ahead of time what your ortho is going to look like before you have to go through the ortho production. So with the DM editor right here, I'm able to visualize and flicker between orthos in one area, or images that are temporarily orthorectified, so I can see what my images would look like with the elevation model that I'm using. And the other quality assurance tools that we have, well, one is the mosaic tool, where we're able to do interactive color balancing using what's called dodging points. So these dodging points, you simply drop them along your seam line, and they're going to automatically gather statistics and color balance your image, as you can see right here in this little graphic. And then the last tool we have that's very valuable as well is the Smart Geofill tool. The Geofill tool can be used on DEMs, and it can also be used on Imagery. And myself, I've been using it quite a bit with Imagery when working with DSM True Ortho products. So I've been using the Smart Geofill tool to sort of refine building edges. So the way the Smart Geofill tool works, it allows you to draw an area in an image, and the tool is going to automatically identify all the overlapping orthos. And then from there, you could scan throughout all these different orthos to find a candidate that's good to sort of paste in that portion of the image. When I'm working on DSM True Ortho projects, with the Smart Geofill tool, whenever I have a building that's not quite right, that's a little bit distorted, I could just draw an AOI around that building, and it will find all the overlapping images, and I could scan through them and then identify a good candidate where I don't have any artifacts along the building edge. So one thing, to sort of review this slide, the reason why I'm going over these QA tools is because a lot of our users and customers have found that these tools are very valuable. They're aerial processing. And it allows them to save a lot of time not having to go back a few steps and pre-process all their data entirely. So another important addition that we've made this year with the aerial package is the ability to generate multi-view DSMs. So being able to, being able to sort of extract multiple elevation values at 1 pixel and then choose what is the most likely realistic elevation value. So the way we do this is using all the different overlap that's available in an aerial data set. We extract all the elevation values, then we apply a variety of different routines and procedures to identify what is the most likely elevation value. So by doing this, we're able to generate surface models that have no occlusion or have very little occlusion and are very sharp in detail. And our ability to generate these surface models is quite important, the multi-view surface models, because this is what allows us to create DSM True Orthos. So using such a high quality surface model, we then have the option to create a DSM True Ortho instead of a traditional DTM ortho. And you can see the difference between the two is quite important. So for one, you don't have the occlusion in the DTM ortho anymore, and this is important. And then the second thing, you'll notice at the top of this roof, the top of this building right here, is geographically accurate. So in this one, it's not because it's leaning. And this one it is. It's accurate. So all of this is possible with the ability to produce these multi-view DSMs. Now, another advancement in our UAV, in our aerial package, is the ability to process UAV imagery. Now, I'm not going to go too deep into this. Stanley is going to talk about that in a moment. But we've done recent improvements to our point collection methods that have allowed us to correct for more sensitive imagery, such as UAVs. So just to give you some quick tests of some data sets we processed with experimental code, here we have one surface model that was produced from the EB at 6.5 centimeters. And this is the mosaic that we're able to produce afterwards, the ortho mosaic. Here we have another data set from the Wingtra. And this is quite interesting because the GSD is 1 centimeter. And here we have the mosaic that we produce for that completely automatically. And then the surface model that we're able to produce. So if we go down even closer, you can see that at 1 centimeters, we have a lot of information available. We even see the head of someone right here. And we're able to extract the surface model of that 1 centimeter data set at 1:1. OK. So one last section, additional 2019 highlights. So in 2019, we have other features coming out, like Sentinel-1 TOPS support. So we've provided the ability to perform the of Sentinel-1 TOPS. And here we have for example, TOPS data with our top scientists. And we've done the debursting, so you can see that our top scientist has been debursted. And then we have another function, new function coming out, star synthesis. And I'm not all that familiar with this one. Actually, Julius, can you quickly? John, John, you're there.
Basically, what it does is it reads the state vectors that are available.
Nope.
Yeah, the process here is that the user would give a data set, and we read the state vectors from that, and from that we compute the orbit and direction of the satellite and the viewing geometry. And with a DEM, we look at the slope and we estimate what the backscattering would be. So we're basically going to eliminate all the effects due to slope effects so that the segmentation will be a lot better.
Ah, excellent. Thank you. And then other notable items in our 2019 release, while we're going to be migrating from Python 2.7 to 3.5 or 6, I believe. 2.7 is now going to be deprecated, so we'll be moving towards the 3.5 or 6 Python. We'll have the object analyst algorithms available in Python. New sensors, new sensors where we've modified our provided new support for is MODIS. We've modified our support for MODIS, GAUFEN 3. We've added support for GOC-TURC 2 and GOC-TURC 1, SPOT 1 to 4, some updated GXL. And then this year as well, in 2019, we're going to have a more advanced integration of the Bingo package for bundle adjustment of aerial imagery. And then we have the new functions, the SAR synth that John just spoke about, and SAR topographic calibration. And new GXL jobs are modules that will be introduced in 2019. We have the super registration, the DSM to ortho, the ability to export data to the Open Data Cube, and we're going to have a new interface for GXL for job selection that you can see right here, where things are going to be, jobs, processes are going to be organized based on their category. Thank you. Any questions? Yes.
Okay, I really liked the demo that you did at the beginning with ARD, so thanks. That was more for multi-temporal data.
Pleasure.
If you were dealing with a situation where it wasn't multi-temporal, but you had a mosaic situation with a lot of data, can you do basically the same sorts of process with that and integrate the mosaicing tool into that?
Okay, so just so I understand, do you mean like if you already have imagery that's stitched together, normalize that's, oh, no? Okay.
So you want to basically create the ARD data from your data. So you go through the steps where you can either point to where the data is, or it can select the data from an API, go through all the steps to radiometrically correct it, and then go through the steps of mosaicing it as well. So in order to be able to get normalization or spectral mosaicing, spectral balancing within your data. Is that possible as well with the same kind of workflows?
Yes, that would be possible. And Julius, do you want to expand upon that?
So basically, the ART correction is applied on an image per image basis individually, while the mosaicing is after that. Once you get all the corrected images in one place, you say mosaic that. I hope it works.
So do I. Thank you. Okay.
Is there any other questions for John? So we'll take a 15-minute break. It's right about 3:30 right now. Sorry, 2:30. So we'll take a 15-minute break, come back at 1:45, and David Stanley is going to give a talk after the break, and then we're going to hand it over to Simon and Cameron for the user presentations. Good job, as always. All right, good to go. Are we ready to go? Yeah, all right. So welcome back, everyone. I hope you enjoyed that short break. It gives me a great pleasure right now to introduce David Stanley, who's our... I was asking David in the broadcast we did last week, how long... Basically since day one. I think he's employee number one. So we're happy to have David. David heads up our science team, and he's going to walk you through what the team's up to. Over to you, David.
Sure. You unmute David.
Oh. Yeah, good to go.
Okay. Am I hearable?
You're live on YouTube.
Okay. So I want to thank you all for coming. I'm very appreciative of the user base at all times, especially after 40 years at PCI. It's always nice to see that we still have lots of users, especially given it's global.
David, we need to hear you. You need to project your voice.
I thought I had a mic. Okay, so I'm delighted to have everybody here and to see all our users from the Ottawa area and a couple of people who came from further away. I'm going to talk today a little bit about what our science team is doing. This gives you a little insight in the directions that we're going in. First of all, we have a science team here, and you have already met Julius and a few others that were in the Ottawa area. Our other scientists are in the Markham office in Toronto. It's interesting, I was just going through this one, looking at the number of years that the people have been working in this industry, and our science team has over 200 years of industry experience. That's quite a lot, right? John Wessels and Gabrielle are our SAR experts. I'm in the DSM and image matching and color balancing. It was areas that I've been working on, and I am very lucky that I actually can hide and do programming still and do actual code and research. Masur, who you met here, is our object analyst father and our feature match or feature extraction expert. Wolfgang and Julius form the core of our ARD team. Wolfgang is actually in Victoria, BC, actually Salt Spring Island. He works from home on Salt Spring Island. That's really nice. But and Dr. Philip Cheng and Dr. Yang Hu are our photogrammetry experts. By the way, I'm going to try to accelerate this slightly because we're running a little behind schedule. I don't want to interfere with our presentations from some of our users. You saw this one. This is our key technology investment areas are alignment and normalization, which are the geometric positioning and radiometric pre-processing. This was gone through by Arnold a little bit, but I just want to re-emphasize all of our work is in these core areas. At the moment, we've been focusing very heavily on alignment, normalization, and feature extraction. Because if you want to do time series analysis and multi-temporal analysis, you need to have the first three ones completed. If you don't have that, then your time series analysis is not particularly useful. So at the moment, we have not had a lot of emphasis on time series analysis, but it's where we're going towards. Okay? I'm going to go into a little bit of the sample research work that we're doing. This is not intended to be a comprehensive coverage of all the things that are going to be in the new release. They're mostly what our scientists are working on at the deep research level. So one of the first things is in alignment. If you're going to do alignment, you need to be able to find the same points on images. So image matching. And we've been very heavily working on that in the last year so that we can do a better job with things like UAVs and super registration. Okay? So we've implemented the SIFT scale invariant scale invariant feature transform algorithm. And this algorithm is really good for finding tie points between images that you have varying scales and rotations. You don't really know what's going on very well in them. On the other hand, it's hard to control the tie point distribution, okay? And sometimes the accuracy and connectivity is a little poor. The other one we've done is improved phase matching, FFT phase matching. This is a core technology we've used in the past, but we've gotten a lot better at it now. And its downside is that it's not so great at scale and rotation, but it's really good at connectivity and distribution. And what we're looking at now is actually using them both in combination in circumstances, different circumstances. I'm going to show you here. This is an aerial project where we've used phase matching, and this gives you an idea of the distribution of the tie points and the reliability of them. This particular project was so good that in the block bundle adjustment, we were finished. There were no blunders at all in this project. And this does mean that when you're starting to do things like super registration, you have a lot better chance of doing a great job. One of the things we've also been working on is UAVs. One of the reasons that we've been working on UAVs is they're hard. Because they are very messy, people don't have good positional information, their rotations, the plane bob, the little UAVs bob up and down. If you can do a good job on a UAV, the satellites and larger air photos are pretty easy. Yeah, they're easy. So we've gone with some of the most difficult stuff. So though we are moving towards handling UAVs, UAVs are not necessarily our big priority. It's just that a lot of the work that we do actually works on UAVs as well. So for instance, here is an example of a data set that we were processing. It turns out that it was a drone, and that's the camera they use. I actually looked up, why do they use that camera? Well, it's because it's really light. High resolution, really light, and a good focal length for the UAVs. So, but that's a consumer camera, right? So here's an example of 300 images, 5 centimeter resolution. This is the mosaic that we produced. What's interesting here is this is an example of the DEM that we extract. The trouble here, what's interesting here is this is not a particularly good one, but we do get multiple angles. So if you see that, these are the two angles that we have. And in fact, sometimes we get 20 or 30 in a particular location. And when you do that, you can clean it up. And that's what you get. And zooming out a little bit, this is like 40 or 50 images stitched together to get a beautiful DSM, even on UAV. Here's an example of a building and another building. You can see the lean, but when we do our true ortho, there it is. And this was 5 centimeter UAV data. We've done this, and Jean was showing you even down to 1 centimeter. Though we are moving towards UAV and our software will process it, it's not a big push yet because we're still working on reliability. That's the thing. When you start going out to the low end people on the UAVs, they want to push the button, it's got to work. Right now, we push the button, and 90% of the time it works, but 10% doesn't. So we're still working on that part. Anyways, more sample research work, normalization. Now I'm going to skip through these ones because they were talked about, super registration. But this is some of our ARD work and radiometric normalization. But I'm skipping through the optical part. I want to go into the SAR part. One of the things that we've been doing right now in research, being able to move between SAR geometry. For instance, right now, when you want to do any work with SAR data, you usually have to take the slant range data and convert it into an ortho product and then use it in that space, in the geometry with other data. Well, the problem with that is when you resample the SAR data, especially polarimetric and other data, into the ortho space, you've actually degraded the information content. So one of the things that we've been doing is we can actually now resample optical and SAR data, other SAR data sets, into the original slant range. And then you can do all your analysis in slant range, especially things like Object Analyst, and you can actually get, we believe, higher quality data, higher quality results out of this, because you're not messing up the data inside your SAR imagery. One of the being able to do this is we could actually project DEM data into slant range. And if you do that, you can see all the layover effects. And so that's really interesting, because it allows you then to remove some of the layover effects to get a higher quality backscatter in the original slant range data. We believe at this point that we're probably the only commercial package in the world that can achieve this. And it's a very exciting area. John Wessels, if you want to know more about it, John Wessels would be delighted to talk to you about this. Some of this is coming out in our next release, and we're very intrigued at this point to see how much better our SAR segmentations and information extraction will get that way. By the way, you can also take optical data, convert it into slant range, merge it with the SAR data, and do your analysis in slant range, okay? This is, for instance, an original SAR image. This is the estimated correction for the slope via the DEM. So that's been projected into the slant range. And then we get an image corrected for slope. So that's a normalized data, right? Better backscatter. This is going to be really interesting with the RadarSat Constellation mission. This type of work was done all in preparation for the RadarSat Constellation mission. Another one we've done was object-based classification. They were talking about that a bit. For instance, the old version in 2018 or previously could only do one small images. Now we can do much larger images and then spread it out to the automation. We've also added a whole bunch of geometric attributes. This is very interesting. We can calculate vegetation indices on the fly. I have to create them ahead of time. You can just select them from a drop-down list. And we've added in texture attributes. This nicely rounds out in Object Analyst all of the attributes you can use. And Masur here has been doing this work, right? And this is coming out in this release. What's next for the science team? Well, we really want to get full UAV support in. So we are working on that. That's something that we're looking at for 2020. 2019, there will be some capabilities. Use it at your own risk, but 2020, we want to be really good at this. And we also believe that in the full processing flow, we can achieve at least a 2 times factor improvement in processing, from all the way from the original alignment to the DSM extraction to the end of the true ortho production, maybe even more. So right now it's pretty good, but it's going to get a lot better. We want to be able to work with really big imagery sizes. 10,000 UAV photos in one project is our objective, for instance. Another one here is that a lot of this work is meant to really help our AARD super registration workflows. In Object Analyst, we are working at expanding out the features so that the 2 big ones you'll see here is to add in the random forest classifier instead of the support vector machine. It's the other very popular one on that one. But we're also already starting to look at the deep learning. We will be integrating in the ability to work with the deep learning. TensorFlow is our expected target package. And being able to have fully integrated GXL workflows that would even potentially include the neural nets. Okay? One last thing in terms of functionality is the hierarchy and expanded rules, so that you can have much more complex interactions between attributes and different types of layers. With this type of stuff put in, we'll be very similar in capability to e-cognition, right? but hopefully much faster. It's a faster and much simpler to use. In the area of SAR, the big thing for us in the next half of the year and coming up into 2020 will be working with the RadarSat Constellation mission. That's going to be really prime. So we're hoping to have support for the RadarSat Constellation mission in virtually as soon as they start having the commercial release of the data. We've done most of the work already. And of course, all the new sensors, and it's very exciting to see what sensors are coming out these days. Once again, John Wessels is our guy to talk to about that. One area, of course, that as a big bugaboo is phase unwrapping, and we will be doing more work to try to improve our phase unwrapping. And John has always pointed out that we need some more advanced visualization tools. So those are the things for 2020. In the ARD, this is going to be a huge area for us in the science team. There is, of course, Wolfgang and Julius, and I expect to join the team too in the latter half of 2019. Really what's happening here is the base work would have been done already, and then we're going to expand that out to a large number of sensors. Now we have maybe a handful, but we expect with the work that we've done to be able to incorporate 20 or 30 new sensors in. We also want to get more robust masks for things like clouds and vegetation classes and add cloud shadow. And this is really useful for creating automated cloud-free mosaics. Okay, so super registered, data normalized, cloud-free mosaics by just pointing to a bunch of files and say go. That's our objective for 2020. And the new thing that we really want to get into is time series analysis. So that would be the big work item for 2020. We'll have done all of the basic work, and Masur, our lead scientist here, once he's finished with the deep learning, is moving over to multi-temporal analysis. Okay, so we expect to have our first set of tools coming out for sometime in late 2020. But right now, we're actually having a bunch of research projects with the Government of Canada looking at time series analysis. So they're starting that process themselves, and we hope to piggyback on some of the research that they're doing. And we have flood risk assessment, urban change monitoring, and deforestation. These were things that Arnold mentioned before that my science team is involved in. And we have other projects that we're hoping to get in the next few months that are even more encompassing than this. So not only will we be doing the development of the tools, hopefully there will be some great research that will be done with them and that we'll be able to leverage as part of our production flows. Anyways, thank you. Anybody have any questions? I'm here the whole time till the end of the meeting, and the scientists with me are as well. So I would be pleased to answer any questions you might have. Thank you. I think I can manage, sort of. I'm good. So I'm just going to clip this on real quick, just for a second. Yeah, I'm not going to talk very long, so I'm just going to pass over. So thanks, Dave, for that. As Dave mentioned, he's been pointing out all the scientists. The conversation doesn't have to occur today. Make sure you get their email address and have a conversation with them. We welcome that and encourage it. The first of the two user presentations that I would like to introduce is with a gentleman named Simon Tozchuk Leclerc. He gave me some pronunciation tips. So I don't know if I massacred it or not.
But Simon is with the Canada Centre for Mapping and Earth Observation. Specifically, Simon is with the Emergency Geomatics team. He is the emergency mapping the role that he's in is the emergency operations lead. And this is a very important group that's been very, very active this year with the floods that have occurred in Canada in both New Brunswick and also here in Ottawa in our own backyard. Simon has a background as a master's in geography from the University of Quebec in Rimouski, and we're happy to have him. So Simon, let's have you come up.
Dans le dossier sur le
Desktop.
ouais, c'est ça. Desktop. Il y avait le work. Ouais, voilà.
C'est là?
EGS, voilà. Hi. So yeah, my name is Simon Tolchuk, and as he says, I'm the ops lead for the Emergency Geomatics Service at the Natural Resources Canada, which is part of the Canada Centre for Remote Sensing that has been mentioned a few times today already. I'd like to first acknowledge the rest of my team because without them and their effort, which there was a lot of on weekends and at night, we would never have been able to do what we have accomplished in the past season, the past flood season. So Ian Oltoff, which is our lead scientist, Thomas Rainville, Victor Neufeld, Philip Muis, Brad Lurbass, our developers and operators, and Vincent Decker, my manager. So that's our team, an all-star team. All right, so what exactly is the EGS? So since 2004, we've been providing emergency response across Canada for numerous disasters. And we've also covered some international events at the request of usually D&D. So we cover a wide range of disasters, and for example, in 2017, a big effort was put together in my department to support the response in Fort McMurray, and so the EGS drawn upon to analyze imagery and collect them. Well, there's a thing that's called the International Charter for Disasters. So when that gets activated, we are basically flooded with imagery from every sensor across the planet, and we got images from the Russians, from Korea, from Japanese, ALOS, and ESA. And so we'll be able to see a few examples of these images later in my presentation for the 2019 floods, because it was activated, but so was it in 2015 for Fort Mac. And so what you see here is basically the burn area in red around Fort Mac, and a new analysis that my colleague Brad Lurbass is working on right now to be able to better identify using coherent change detection in order to be able to see which buildings have been affected in the various neighborhoods of Fort Mac. And so that's a few graphs that he kindly gave me for my presentation. And so this is one of the upcoming projects that it's not operational yet, but it's kind of the future, and we're again really hoping that the RCM will enable us to use to put these methods to good use in future events. Another event that we were tasked on was the tornado in Ottawa this past September, right? And so, as you can see on this map, there were actually two tornadoes, and one that traveled a bit more to the south near, I think it's Kanata and Nepean over there. And another one that traveled across the river from the municipality of Dunrobin all the way to Quebec into Aylmer and then eventually Hull. And so these are in response again to that event, Public Safety Canada, which is our main client, let's say, has tasked the NASP, or the National Air Surveillance Program, that is operated by Transport Canada, to fly a surveillance plane over the impacted areas. And so our team, it was really in Hull, hands on deck, good old photo interpretation, because these images are not, they're geotagged, but that's it. So that would be a good problem to tackle in the future, but how to be able to auto-rectify these images. But in the end, we were able to assess the damages, and as you can see, well, it was quite extensive. Another of our, let's say, the best, or the product that we are known for, and we do push out a lot of those, are our river ice monitoring products. And so we do that in collaboration with the provincial public safety authorities that request that to Public Safety. Some provinces have a capacity of their own, but some don't. So for example, back in 2016, we transferred our river ice mapping technology to the province of Ontario, and now after a 2-year pilot project, they are now operating the system on their own using radar sat images again. And so this year we continued the monitoring. So that example there is an ice map. So in pink, what you see is an ice jam, or a rough, very rough patch of ice, or ice that is like made up of blocks that are traveling along the river. And the aerial image in the corner is an image that was captured by OMNR while they were flying to better assess the situation and eventually decide if the community, the First Nation community of Moosonee or Fort Albany, and eventually Adowa-Piscat, that should or should not be evacuated. And so this year, thanks to the technology that was developed, and the monitoring that OMNR does, they were able to forecast a severe risk of ice jamming and flood, and so they evacuated the Adowa-Piscat communities. And so we did maps for Manitoba and New Brunswick this year, since we don't have anymore, and we just we're at the ready if Ontario needs it. So all of that wouldn't be possible if CCMEO wasn't also operating the satellite receiving stations. Oops, sorry. And so basically we operate 3 receiving stations, Inuvik, Prince Albert, and Gatineau, plus the archiving or data access system. So that's the CGDI group, that's part of CCMEO and NRCan. And so those satellite stations are obviously critical to our operations and many other departments too. But what the product we are most known for is probably our flood maps, which I am here to talk to you about. So what you see there is an example of one of our flood products we did for the province of Manitoba. But in my presentation, basically I will show you a bit and tell you about our mapping algorithm, and then I'll briefly touch upon how our production system is set up, and I'll end up with the good part, the examples from the 2019 floods. So our algorithm takes 3 inputs. First one is the historical inundation frequency, a SAR scene that doesn't necessarily have to be radar sat. As you'll see, just the SAR scene could be TerraSAR-X or ALOS or any other sensor works, and land cover. So other researchers in our group provide the land cover for us, so Racine Latifovic, and we source the historical inundation frequency from the work that was done by Pickle and so in a nutshell, basically From the inundation frequency, we are able to derive a permanent water mass that we can use to train our C5 algorithm, classification algorithm, and using the land cover, we are also able to train the C5 classification algorithm on what is not water. So at that point, we eventually end up with an open water classification, and then we do some region growing around the water that have been classified as water to be able to identify flooded vegetation. Then the last steps are, well, infilling the flooded vegetation areas. As we receive the product a bit more pretty and accurate, and eventually we vectorize and go on with publication. So what we do, we try to exploit the useful information that's embedded in the past, right? So using those water occurrence maps, we know where water has been, and we can use that to be able to know where the water might occur again. And so using a sampling mask, we generate training areas for all of our different radar scenes. And in the end, so basically using RadarSat, you would see that the black areas there, well, they do correspond to the lakes that are in blue in this water mask. And using our machine learning classification algorithm, well, we can eventually come up with an open water classification. And so from that point on, that's we exploit the fact that the flooded vegetation generates double bounce, or basically when the radar waves are emitted from satellite, right? They will bounce once on the water surface and a second time on the trees. And so if the vegetation wasn't flooded, it wouldn't be as bright as other vegetation patch, right? And so what you see on that image there in bright in the middle, it's basically the white stuff is the flooded vegetation. And so from there, since we already know where the water is, because it usually is very black in radar images, and it's kind of easier to map out, well, we region grow into the flooded vegetation using thresholding, and we do several iterations of that up to 200, and then we in-grow first outward and then inward to make sure that there are no holes left. So basically there are two sets of thresholds where you make sure you get all the way to the border, and then you infill and try to take out those darker vegetation areas. And so you end up with a map like that gives you open water and flood veg and land. Now let's say we want to dive a bit into detail. So I told you that the method works on multiple SAR sensor. It's true, but it's not exactly true when it goes down to polarization. So basically our method works way better when HH polarization and or HV, depending on the or the scene setting at the time, right, in the field. But so as you can see on HH on the left, the contrast between flooded and unflooded vegetation and or land is way higher than it is on the right, which is a VV scene that's just taken a day after, which both of these scenes are Sentinel-1, just different polarization. So our algorithm is, well, better able to extract that bright area when it's HH. So the end product would be, again, a flood map where we add region grow, and we are able to capture the full flood extent from that scene. In this case, it's a RadarSat to HH polarization on the same day as the other one. So there are a few errors that can affect our classification algorithm, but thanks to the C5 algorithm, well, basically even if the training sample is not perfect. It can accept really up to 30% training error before starting to really degrade in terms of classification accuracy. And then once you go past, 50%, well, it doesn't work at all. But in our case, we get very good values for open water, and it's pretty accurate. So how did we go from, well, basically that science and those principles to actually putting that in action? Well, most of our systems, our tools are coded in Python, and our tech team basically needed a graphical user interface, so to make their life a bit easier. So basically we leverage ArcPy from ArcGIS Desktop, and so the core of most of our tools are Python toolboxes that call PCI routines from the Geomatica API. And then from there, we wrap that up into Python toolboxes and Python tool and ArcGIS toolbox, because our users are accustomed to that. And so our system goes from basically we ingest the data, and then we generate orthos and yada yada until we eventually vectorize and the data set. So 2 years ago, we implemented a data production system that's based on Postgres SQL database, and now in the future, what we want to do is that we want to. So as you can see in green, a few boxes have now GXL written in green by them. So this season, we've been able to use GXL to to run our flooded vegetation algorithm and our river ice algorithm. It's just that it's not completely automated yet. So our vision for the future is that we'll be able to leverage the GXL capacities to make our system more automated. So by GXL talking to the our production tracking system, which is on our Postgres database, we'll be able to have basically the whole system just waiting for images to arrive, and then it will know what should be coming in, either through basically what we need to do is mostly set up the acquisition plan in the operation tracking table, and then once that's set up and that we integrate either through KMZ or shapefile in our main operation tracking system, we can then launch we will want to be able to track the production and just like have a look at it from afar and only do QC QA at the end. So yeah, I think I've already covered most of that. So in 2019, flood season, we were activated for 3 areas in Quebec, the Ottawa and west of Ottawa region, Montreal, Lac-des-Deux-Montagnes, and Lac-Saint-Pierre. So the activation, let's say, or the call from public safety came around the end of the month of April on the 20th, and soon after the International Charter for Disasters was activated. And like this year, because 2017 was such a big flood season, everybody was really ready for that one, and so we didn't waste any time and started acquiring data with all the sensors that we could, knowing that the peak would come quite fast. So basically the peak came on May 2nd, and it peaked around 10,000 meters per second, 10,000 square meters per second at Carillon. The forecast we had at the time was 9,400, so which was like a bigger value than what it was in 17. And for example, today the discharge is at 3,400 cubic meters per second. So that's quite a bit of a gap. So the water rose up all the way through almost 45.5, I think, in Gatineau, and so basically the authorities were wondering, well, where is the water? Where could it go? And so in this image here, what you can see is one of the first map we created using our first optical image that came in on it's a Pleiades image that came in on the 22nd, and a radar sat image that gave us a better overview of actually what was going on everywhere, because the Pleiades image was very small. This is it was mostly cloudy, but we had a good look on Point Gatineau, and so we kind of created a hybrid product with for this map. And so that's just a close-up of the Pleiades image. Then a few days later, on the 26th, we received another radar sat scene that we used to map really the whole and most specifically the Constance Bay area. So this product specifically was used to brief the Prime Minister when in his when he visited the Constance Bay area on the 27th. That one I worked until 1 a.m. to push out. And so after that, lucky for us, we had some Planet account that was shared with us. So we were able to acquire some rapid eye images over the Point Gatineau area, and you can see how the flood has progressed in basically 6 days, right? And so most of the areas that weren't flooded on the west side of the Highway 50 are now flooded, and most of the Point Gatineau area is now completely impacted. And so that's kind of one of our best product that's nearest to the peak flood. I've put here another product that's quite close to the peak flood. Around the more the eastern part of the Gatineau area. So what you can see there is quite a few areas of flooded vegetation in white, and even some more the lakes and kind of not lakes, but yeah, lagoons from the river in a way. And so our classification shows them permanent channel in light blue. In dark blue, it's the open water flood, and in green would be the flooded vegetation. So again, the same area, but on May 7th around Gatineau, and now you can can't really start to see receding in the center part of Gatineau, but you are able to see it in the Constance Bay area. By the 7th, the water was starting to come down a bit, and eventually in the central part of Gatineau too. So this is another product we created over Constance Bay on the 29th. This one using Terrasar data. I can't remember the name of the beam mode, sorry, it's the high resolution one. So it was a pretty good product, pretty accurate. The next image is over Lac Saint-Pierre in Quebec. So again, using radar sat data, we were able to map out the Lac Saint-Pierre area, which is kind of the St. Lawrence River in a way, and so there was way more flooded vegetation in that part, and the Highway 40 always remained they're drivable or truckable, but that's one of the challenges for us to be able to make sure that it is. So sometimes we use alternate imagery to confirm that. So again, that's a Pleiades image we got from the International Charter over the same area, Lac Saint-Pierre. And for the optical imagery, though, it's a bit trickier to be able to map the flooded vegetation. So we are able to map some of it and region grow in it a bit, but it's not as easy as it is in radar images. And so that's the Lac des Deux Montagnes area in Montreal. And so you can see that, the most impacted regions are Sainte-Marthe, Oka, and Rigaud. And that's the region of Rigaud. And so that's an aerial photo. Again, NASP was flown. And you can see here an example of what flood vegetation looks like when you're looking at it from a plane. And so in red, it's the area that's covered by the picture, right? So in this image, you can see the flood progress between April 20th to 25th. And the ALOS imagery on the right is also very effective at mapping the flooded vegetation because of the longer wavelength. It's a bit more effective to penetrate the vegetation cover. That's a very good image we got over Saint Martin where the dike broke. So in dark, it's basically the flooded area of Saint Martin. And for that one, we did use some region growing algorithm, but eventually we had to do most of it by manually just to make sure, because it was a high priority product again, and the Prime Minister of Quebec was briefed with the end product. Not with our templates though, because usually Public Safety Canada takes our product, or Quebec will take the end product and put it in their own maps. And so that's a close-up of what Saint-Martin-sur-le-Lac looks like in that image. So 6,000 people were affected by that dike. And most of them weren't even close to the water, didn't know they were in a flood zone. So I told you about the 3 areas in Quebec, but there were some floodings at the same time happening in Fredericton and St. John in New Brunswick. And so basically we created some flood maps over there too, and the flood vegetation is again a big problem in that area, as there is a lot of it. And so that's a close-up on Fredericton on the 27th. And at first this year, usually the floods go from the west, and they kind of tend to migrate. Like it starts in Red River, then Ottawa, then New Brunswick. But like this year, it was all at the same time. It was the first time that we had that many areas of interest to map out simultaneously. And so again, a product of Manitoba. We followed that beginning in March, because we saw the news report from the floods happening in North Dakota and Minnesota, and public safety was really well concerned that it might travel up. So but it did a bit. So as you can see up top, it's the town of Morris that's in Manitoba, but really it kind of stopped there and never it just eventually flew in Lake Winnipeg. Not flew, I meant went away in Lake Winnipeg without creating much problems after that. So how can you access all of these maps if you wanted them? Well, the first way to do it would be to just either Google NRCan flood. You're gonna land on that page, which is you'll find every link that you need. There's also an Open Maps, and from that page we link to our Open Maps collection of products. So we have two. We have the flood collection and the river ice collection, and from there if you click one of the links, you'll be able to be redirected towards our different resources, be it REST services or web mapping services, file geodatabases, and all of that. And if you click the little view on map, you see Open Map Data Viewer. So if you click that, you will be brought to the interactive map that comes bundled with the Federal Geospatial platform. And if you click on any of these polygons, you'll be prompted with a direct download link that links to our operational FTP download site, which is number 3 on there. So in a nutshell, we produced 86 different products this year, 25 of which were with international chartered data sets, using SAR, optical, over 20 different AOIs in total, and 55 of these products were flood products. and it was one of the biggest year on record. The second biggest after 2011. So thank you, and can't wait to get some RCM data.
It's okay. Not sure if Simon, if there's any questions for Simon. He kind of walked away really quick there. Yes, question.
Simo, thank you for your presentation. A couple questions. One that looked like I forget the name of the town now, but there's a town just west of here that got hit in the fall by a tornado and then in the spring by a flood. Dunrobin.
Yeah.
Did you overlay the two maps and see where the?
No, we did not do that. But maybe it would be a good idea to.
Yes,
Yeah.
exactly.
I heard of a family in Gatineau. Well, they were in the newspaper where they were hit by the tornado in Gatineau and moved, and then were hit again by the floods. they were really fed up, poor folks. Yeah, I hope. Well, at least the public safety has programs in place to help them out, right? So
I have a second question. That's more to the data and your methodologies. You said there were three main inputs to the process. The first one was historical flood maps.
Mhm.
If you took that data product out, how good would your maps be? And I'm trying to get a sense for the value of the historical information.
Well, it's very important, let's say. Yeah, it's one of the critical piece of information. Unfortunately, I cannot speak that much about it. It's more as it was developed by my colleague Ian Oltoff, and I wouldn't want to say things that he wouldn't agree with. But I think that, well, it is fairly important in our process, and right now we cannot do without. But one thing we are working on, though, is we're doing our own improved flood frequency map using both optical imagery and radar imagery, and this is actually the projects we have in the works with PCI. So our goal is to leverage GXL and DataCube technologies to be able to create those flood frequency maps that would be more accurate than what we see right now, because flood vegetation again is an issue in optical, and so that's we saw that in Pickle's product, and we're trying to improve that in our own. Oh, sorry.
Have you considered using a digital terrain model as one of the inputs to the process?
Yeah, of course, digital terrain model are inputted to create the orthos. In the future, we want to use LiDAR DEMs to be able to better map urban areas, because these areas are right now, if we don't have an cloud-free optical image, it's really hard to map them with radar. So our goal would be to work on a hybrid approach, where we'd be able to leverage both the high-resolution LiDAR DEMs and the observation from, let's say, a radar satellite, in order to be able to infer, let's say, water level and apply that in the LiDAR data, maybe.
Keep you busy off-season, acquisition and building of database of actual floodplain mapping, at least in major urban areas.
Yeah, we have another group in Sherbrooke that is working on creating hand LiDAR models, height above nearest drainage, that we are hoping to be able to leverage in our operations. So we're working with them on that. And there's also the National Floodplain Mapping Strategy that is also piloted by our office in CCMEO. And so where we recently received some money in the budget to be able to acquire and put out guidelines and acquire data. So.
Merci. All right, well, thanks very much, Simon, for that presentation. What's very exciting about that project is not only is the GXL being used in Canada for doing big data production, but it's a turn towards science, which is the direction that we're going in as a company, as you've seen from some of the presentations earlier this afternoon. And to hear Simon talking about flood frequency products, leveraging those deep temporal archives is something that we're excited to see. That's a good segue to our next presenter, which is our last presentation of the day. So we have a presentation from Cameron Sampson, who's presenting on behalf of Environment and Climate Change Canada, specifically the Pollutants Inventory Reporting Division. Did I get that right? Yes. That's a very important division. They actually hold the ball in terms of Canada's responsibility for the use of Earth observation for reporting on carbon accounting within the International Climate Change Accords that Canada is a signatory party to. So a really excellent team of scientists is working on leveraging Earth observation technology to aid Canada's efforts to understand climate change. And so Cameron is a graduate of Carleton University, has a master's, and he is a physical research scientist currently working on carbon emissions. So come on up, Cameron. Just ask you to bring that in. Sit you up here. You have to escape out of it.
That's okay. Yep.
Oh, you're good.
Perfect. Okay, thank you, Kevin. So I'm going to keep this a bit shorter, being time, but that's okay because we're going to go over some stuff. So I'm going to present to you guys the hypertemporal monitoring of urbanization using the Open Data Cube in Canadian cities, and it's a project that we're working on with PCI. So just a bit. So the National Greenhouse Gas Inventory is an international reporting obligation. As Kevin said, we have signed with the United Nations Framework Convention on Climate Change, so the UNFCCC. And this here is a national greenhouse gas inventory of emissions by sources and removals by sinks, and it's prepared annually, so this is the report we give to the UN. And in 2019, it was our 26th edition. So a bit about my department. So I'm part of the Pollutant Inventories and Reporting Division. We have 3 reports: the Greenhouse Gas Inventory Report, the Air Pollutant Emissions Report, and the Black Carbon Inventory. So the Greenhouse Gas Inventory is a flagship product. It's the official national report of anthropogenic greenhouse emissions and their trends since 1990. It's an authoritative source of information and data for the entire Canadian economy. It's science-based, transparent, and documented. The inventory plays a pivotal role for supporting domestic and international policies. So a bit about the report itself. It's a time series coverage from 1990. So this inventory has estimates for 7 greenhouse gases, such as carbon dioxide, methane, nitrous oxide, and others. And there's always continual improvements because it's a key principle. With improvements each year, the historic inventory estimates are often revised for many reasons. This could be just refined data, recommendations from the UNFCCC, or implementing a methodological change, which is what I'm going to be talking about a bit today. So just a quick overview. There are 6 divisions. I'm part of the agricultural and the land use change, and forestry division. And all that information gets sent to the quality management and verification, which when there we put a report, and then that's domestically reviewed and verified. And then we send that over to the UNFCCC, where they have expert reviewers, and they take a look at it there. It's also supported by an extensive national network, so Statistics Canada, Transports Canada, Natural Resources Canada, Agriculture and Agri-Food Canada, consultancies and industry associations, and there's data sharing agreements and MOUs, and that gets all sent to us, and then we make a report from that. So here's just an example of the trend for our inventory. So we can see here that it's an increase over time, and it often follows our economy, and that's why you can see the dip over in 2009 when we had the financial crisis then, and then it's slowly been increasing again. So obviously humans alter the natural carbon cycle. For land management, you've got forest management, cultivation, and urbanization, which I'm going to be talking about in a bit. And then for land use, we've got deforestation, drainage, and flooding. And what's important to note is that all of these things cause a change in carbon emissions. And also, we're in Canada, so it's a scientific challenges because it's large. The improvements in the understanding and methods of carbon emissions must be updated, and information comes from many different sources, and there are also gaps currently in inventory, such as the urban expansion. So a bit about it, the land use, land change, and forestry, so LULUCF, is estimates for represent carbon for each land category. Different land use changes represent different changes in carbon. So here are just 6 of our different categories, and I'm mostly just going to be talking about urbanization, so obviously something like a forest being converted into a settlement of changes in carbon emissions. For urban expansion, it's taking place at twice the rate of urban population growth, and these changes can result in either a loss or gain of carbon. So a loss would be something like a forest changing to a settlement, but a gain could be like an agricultural field that's being tillaged, changed into a park, and so we actually have a gain of carbon. The lack of estimates from this source are recognized as a gap in the Canada's reporting of emissions. In order to fill this gap, we need to use a long continuous data set for all of Canada, something like Landsat. So we're going to use Landsat because it covers from 1984 to present. And we're going to be concentrating first with 56 of the scenes, and these cover the 16 central census metropolitan areas that we're going to be looking at. And then eventually we're going to want to upscale to the entire national scale, but we're obviously going to need a big geospatial data analysis framework, so something like the Open Data Cube that you guys have heard about today. So as you said, it's an open source framework that creates an analysis-ready data. And with the help of PCI and their GXL system, we're developing a system to ingest, index, process, and analyze all the data at once and hopefully automate the process. And since it uses Python, it allows us to use and process the data with Python's vast library of different algorithms and something like the continuous change detection algorithm. A bit about this algorithm is it uses all the available Landsat data for the entire area that I'm looking at to estimate time series models. These models are composed of harmonics that capture the cycles and seasonal components of Landsat data. So this will allow us to look at an area and gather all the information from that one, and then we can create these models, which I'm going to show you in just a second. But when these models encounter a break, it classifies that break period and begins a new time series model. They're often caused by land use change, such as an agricultural field being converted to settlement. This system will hopefully give us the tools to analyze land cover changes from urban expansion in Canada since 1990, because we currently don't have that capability. So here's an example of 3 different Landsat scenes. So we have September 1990, September 2000, and September 2010. And then you can see in the bottom left is just the general trends for your bands from your Landsat. And it's hard to determine that there's any change from there. But when we apply the continuous change algorithm, we can obviously see that we've got a nice pattern in the first and the second. And then obviously you can see the break here in 2010. And it's important to notice, but there's that this is representing an urban area, so it's probably right about here, where you can see there's no urban in 1990 or 2000, but in 2010 there's an urban change. So the idea is we want to create these breaks, and then from those we can create a classification throughout time and then estimate biomass measurements. And then we can get something that looks like this. So obviously the light green represents old, so 1990 and little change, where the yellow it represents medium change and around the year 2000, and then red represents recent 2010 and high change. And so you can see that it really highlights where the urban expansion has occurred and where it's occurred recently. And these are just a bit more, this is all for the area of Toronto, just so you guys know, for just a small section. So this statistics, and we can see that agriculture and forest are the 2 main classes that have really changed in the last 30 years. So our future work is we want to add RCM and Sentinel-1 and 2 and other data into the Open Data Cube, because we're currently only using Landsat. validate our results, and then obviously develop a type of storage solution for the Open Data Cube for scaling up to the entire national level, because it's a lot of data and we currently don't have that infrastructure in place. And then we're working with the University of Waterloo to calculate the carbon biomass estimates for the conversion of land use classes. So the idea is to be able to classify when these changes happen. And then once we classify those, we know, okay, it went from agriculture to settlement, what year that it happened, and then what are the biomass values for that. So we have a couple other different projects for remote sensing in the division. One was our mines project. So mines obviously produce dust from the tail, and this is very important for the air pollutant emissions inventory. Before this project, the data was only from one old data set from 1980, and it was used with a growth factor, so our values were not very good. But using remote sense imagery to measure the area of open mines along Canada, and using indexes and a supervised random forest classification, we can now monitor the mine size, the expansion, and the recovery over time. Another project is a peatland project that we have in the works. Peatlands are a carbon sink, but the question is, can peatlands continue to act as a carbon sink under warmer and wetter climate conditions? Past monitoring of peatlands has shown that lateral expansion of peatlands, bog to fen conversions, and greening. So this is an increase in vascular vegetation, so just more shrubs and stuff in the bog. But the goal is to develop a big geospatial data analysis method to extract time series trend data and using Earth observation imagery. We want to characterize the wetland ecosystems, develop a wetland type, and then to identify ecosystem shifts and relevant changes over time. And then we have a few other projects, such as estimating woody biomass for mixed wood plains, measuring methane from flood lands across Canada, and then Norman disturbances in carbon emissions. So in conclusion, the National Greenhouse Gas Inventory is an authoritative source of information and data on greenhouse gas emissions for the entire Canadian economy. It relies on rigorous methodological and quantity standards, builds from an extensive network of data providers, provides transparent and documented assessment. It's updated every year, supports numerous analyses, and supports domestic and international policies. And obviously, we can improve it with remote sensing. Thank you.
Going once, going twice. Thanks for putting us back on time.
You're
Speed talker. That was rapid. All right, so thanks very much for that. That brings our user group meeting to a close. We'd like to thank you for being here. We would like to just make a few kind of notes, I guess. So this is part of the GeoIgnite conference, which is the first ever such conference. It's happening tomorrow and the day after. We're exhibiting at the conference, so we're going to be here. There's other people, actually. Cartavista's here. They're going to be exhibiting as well. Pacific Geomatics is also exhibiting. So Matt from Pacific Geomatics. Anyone else? Esri sponsoring? Esri sponsoring and exhibiting?
Career Day.
Career Day. Clark Lawler from Esri is here. Anybody history that I've missed? I think that's it. Hopefully you all come out to that event. Tonight there is a social event that's being sponsored by Maxar. I think it's at 7 o'clock at the Heart and Crown in the market. So the one across from the parking garage. If you're from Ottawa, you know where that is, downtown. I think there's only one Heart and Crown in downtown Ottawa. So that's at 7 o'clock tonight. Otherwise, tomorrow starts pretty early. I think 8 o'clock. The show will be open. So all of our here, a lot of our staff is here. Hopefully you had a chance to say hello. You don't have to all run away. It's only 4 o'clock. If you want to catch their email address, if you want to continue the conversation, we definitely encourage that. And once again, we'd like to thank you, and we'd like to thank all of our presenters today. So thanks.
the meeting instead of wearing my biking clothes here.
Did you go to Cogs?
What?
How do you know Tim? From out, you went out east? Oh, I didn't know that. You're from out east? That explains why you're so nice.
That's right. Yeah.
That's the right thing to say, right?
That's what we want to hear.
Muted. Is this muted? Not muted.